Imagine your critical system crashes during peak load. Millions of in-flight transactions could vanish, potentially costing your business a fortune, as seen with Knight Capital's $440 million loss. This isn't just a nightmare scenario, it's a real threat that every distributed system faces. Today, we're going to master the fundamental safety net that allows systems to bounce back from failures as if they never happened: checkpoint and rollback recovery. By the end of this lesson, you will be able to understand the importance of checkpoint and rollback recovery in maintaining system resilience and data integrity. You'll learn the different checkpointing strategies crucial for distributed systems, each with its own trade-offs. We'll also explore advanced recovery patterns like the write-ahead log and the Saga pattern, which are the backbone of robust systems. Finally, you'll grasp practical implementation insights and a comprehensive production checklist to confidently deploy and manage resilient applications. Let's dive in. At the heart of effective recovery lies the challenge of consistency. It's not enough to simply save data. You need to capture a snapshot where all components of your distributed system are in a causally consistent state at the exact same moment. This means if service A depends on data from service B, both must checkpoint in the correct order to avoid an inconsistent recovery. Most engineers miss this critical detail. There are three primary strategies to tackle this. First, synchronous checkpointing, where all components pause and checkpoint simultaneously. This offers high consistency, but can impact performance due to coordination overhead. Second, asynchronous checkpointing, where components checkpoint independently. This provides better performance, but requires more complex mechanisms to guarantee consistency across the system. And finally, incremental checkpointing, which only saves changes since the last checkpoint. This minimizes overhead during operation, but can lead to longer recovery times as more changes need to be replayed or undone. Every robust production checkpoint system builds upon the principles of the write-ahead log or WAL. Think of WAL as an immutable, durable ledger. Before any state is modified, the change is first written to this log. This simple yet powerful concept enables both forward recovery by replaying committed operations and backward recovery by undoing uncommitted ones. PostgreSQL's WAL system is a perfect example, ensuring transaction durability. For complex business processes spanning multiple services, modern systems integrate checkpoints with the Saga pattern. Each step in a Saga creates a compensation checkpoint, allowing for precise rollback to any transaction boundary if something goes wrong later in the sequence. A rarely discussed but critical issue is the phantom read problem. During a rollback, other transactions might inadvertently read partially rolled back state, leading to inconsistencies. The solution requires careful ordering of rollback operations and proper isolation levels. These recovery patterns aren't just theoretical. They're the bedrock of some of the world's most resilient systems. Take Netflix, for instance. Their chaos engineering platform deliberately injects failures to test checkpoint recovery, revealing that automated rollback decisions consistently outperform human operators during high-stress incidents. They use progressive rollback, minimizing the blast radius. Google Spanner achieves globally consistent checkpoints across continents using TrueTime, a technology that waits for clock uncertainty windows to ensure causally consistent recovery across time zones. Their innovation includes parallel recovery streams, slashing recovery times from hours to minutes. High-frequency financial trading platforms utilize hot checkpoints, which are continuously maintained parallel states that can instantly become primary during failures, achieving sub-millisecond recovery times, which are absolutely critical in financial markets. And remember, observability is key. Instrumenting checkpoint latency, rollback frequency, and recovery time allows you to proactively identify and address system stress before it becomes a crisis. To truly build systems that recover gracefully, you need a robust production checklist. Before any checkpoint, validate that all transactions are either committed or clearly marked as in flight, and ensure dependent services are in consistent states. Always check disk space, planning for at least 3 times your current memory usage for checkpoint storage. Crucially, test your recovery process under peak load conditions. Verify data consistency after partial rollbacks and measure your recovery time objective, or RTO, and recovery point objective, or RPO, under various failure scenarios. For monitoring, track checkpoint creation latency, aiming for under 100 milliseconds for in-memory systems. Alert when checkpoint intervals exceed twice their normal duration, as this often signals impending system stress. Your challenge now is to build a distributed task processing system with checkpoint recovery. When a worker node fails mid-task, the system should roll back to the last checkpoint and redistribute work. Master these patterns, and you'll build systems that gracefully handle the inevitable failures of distributed computing, allowing you to deploy with confidence.